Oligonucleotides are composed of specific sequences of nucleotides, usually 10 to 150, that are often chemically modified at precise positions within the sequence. The general structure of an oligonucleotide sequence is shown here and is usually modified at the highlighted positions. Oligonucleotide therapeutics represent a rapidly growing new class of drugs that operate by a range of mechanisms, such as antisense oligonucleotides, siRNA, and gene editing such as CRISPR. Interest in oligonucleotide therapeutics has recently increased exponentially, as evidenced by the approval of 15 oligonucleotides over the past 4 years, as compared to only 6 approved over the previous 20. Oligonucleotides are usually synthesized by solid phase synthesis, where the sequence is established a single nucleotide at a time using phosphoramidite chemistry. However, solid phase synthesis relies on huge volumes of organic solvents and a high excess of reagents to be successful. A useful metric for assessing the sustainability of manufacturing is the process mass intensity, or PMI, defined as the quantity of raw materials divided by the quantity of active pharmaceutical ingredient. A recent study estimated the PMI to be approximately 4,300 for oligonucleotides, of which 43% is organic solvents. This represents a huge amount of waste generated during oligonucleotide production, and in this work, we aim to address some of the environmental challenges of oligonucleotide synthesis, particularly the large solvent consumption, by synthesizing short oligonucleotide fragments using resonant acoustic mixing, or RAM. RAM is a unique and scalable mixing technique that has recently been used to carry out mechanochemical reactions. Like other mechanochemical methods, such as vibration ball milling or twin screw extrusion, RAM can be carried out without any solvent in neat reactions or with small amounts of solvent in liquid assisted reactions. RAM functions by shaking materials at the resonant frequency of the entire system, around 60 Hz, with energy input modulated through changes in the vertical acceleration of the reaction vessel, usually measured in units of g, or the acceleration on Earth due to gravity. A typical acceleration used for a RAM process is 60 g, but this can range from 1 to 100. This allows the system to maximize the amplitude while simultaneously minimizing the power consumption. Additionally, since mixing media are not required, scale-up of RAM processes should be straightforward. Using our custom-designed sample holder, we are able to rapidly screen and optimize a range of variables, such as reaction time, acceleration, and equivalence of reagents. Using modified H-phosphonate chemistry, we are able to synthesize DNA dimers in 81 to 90% yield while reducing the solvent consumption by up to 90% during the reaction. We were able to apply this strategy to other therapeutically relevant nucleotides, such as RNA, 2'-fluoro, and 2'-O-methyl nucleotides in generally good yields. We successfully scaled up the strategy to multigram quantities using a Teflon vial and expanded it to include the synthesis of a trimer, as well as developing a strategy for the synthesis of sequences with both natural phosphodiester and phosphorothioate backbones, which are vital for therapeutic applications. In addition to H-phosphonate couplings, we also investigated the use of RAM for a phosphoramidite coupling strategy. After optimization, we were able to couple both DNA and RNA nucleotides in generally good yields, followed by oxidation in solution. Throughout this work, we were able to conveniently monitor our reactions using phosphorus NMR. In this work, we showed the first use of RAM for the synthesis of oligonucleotide fragments, which reduced solvent consumption by up to 90% during reactions, and we found it to be generally scalable. This is just a brief summary of our work, and we invite you to read our publication for more information, which is now online. Thank you for your time.